Right, so starting the recording for everyone watching on the catch up. So what we've just done so far is do a little starter question. So you might want to have a look through this and just double check, maybe pause the video here, just double check this all makes sense, because we are going to do a lot of graphical work in the next few lessons. So it's really important we've got the basics down here. So the topic that we're moving on to today is called the modulus function. Now you would have met this before when we've done vectors, and we've done also when we did binomial as well, you would have seen this modulus function, but we only kind of briefly touched upon it. What the modulus is, and sometimes we call it the absolute value or the magnitude, which you might be used to using when we've done vectors. So the modulus of a number, let's say A, is the non-negative numerical value. Basically what it means is we just ignore the negative sign, okay? And we only ever consider it to be positive. So the modulus of 4 is still 4. But the modulus of -4 would also be positive 4. So what we do is we always just ignore the negative sign there, okay? But it's only what we only work on the bits within these lines here, okay? So lines either side, that is what we call the modulus or absolute or magnitude. Think about when we've done vectors, we're talking about the magnitude, we're talking about a distance. A distance can only be positive. And later on, when we do some work in mechanics next year, we'll also look at, when we're looking at things like distances, speed, scalar quantities, that we just want to take the positive value. So just working through a few of these examples, our first example, f of x equals the modulus of 2x minus 3 minus 5. So firstly, we're going to do this for when x is 6. Okay, remember f of 6 just means replace your x with a 6. So firstly, within the modulus, I'm just going to do 2 times 6 minus 3, and then I have to take away that 5. Okay, so within that modulus, I just get 9. Okay, 2 times 6 is 12, take away 3 is 9. So the modulus of 9 is just 9. So this simply is just going to give me an answer of 4. Okay, the modulus of 9 is still 9. So really, there was no difference there having that modulus in there. But let's have a look at our second example. So we look at f of minus 3. And what I'm going to do there is just do 2 times minus 3 within that modulus, and then I take off the 5. Okay, the 5 doesn't have a modulus sign round it, so I just treat that as a -5 still. Okay, within this modulus, I do 2 times minus 3, take away 3. Well, that's going to be -9, and then I have to take away the 5. So I work out the modulus of -9. So I just ignore that negative sign, just make it a +9, and then I take away the 5, which will also give me 4. So you can see there, I've subbed in 2 different numbers and I've got different answers. With this question, if the modulus lines weren't there, then you would have got a completely different answer. You would have got -14. But because the modulus signs are there, we end up getting +4. Then let's look at the last one. We're going to do 2 times 2 minus the 3, and then we minus the 5. So 2 times 2 minus the 3, well, that's just 1. Then I have to take away the 5. The modulus of 1 is just 1. And then I take away the 5. There's no modulus there, so I still treat that as a -5. So this would just be -4. So what we're going to do today is mostly focus on the graphs of the modulus function. And for a lot of this, I am going to be switching to GeoGebra to show you, which I'll do in a second. But just the key points here first. When we sketch the graph of y equals the modulus of f of x, what we do is we just sketch what f of x would look like originally. So if the modulus lines weren't there, we just draw what the graph would normally look like. Any part of the graph that's below the x-axis gets reflected, okay, in that x-axis. And that's because when we find the modulus, we just ignore the negative. So we're just going to reflect that, and it's just going to be the positive parts that we put there. I'm just going to quickly go to the chat, just check any questions. So what I'm going to do now is I'm going to show you these 3 examples that are in your booklet. I'm going to show you my sketches at the end of this, but I'm going to go over to GeoGebra. So I'm just going to have to stop sharing my screen a second. And share my GeoGebra screen. So hopefully now you can see this. Let me know if you can't see the screen. So I'm just going to go through the first 3 examples. So examples 2, examples 3, examples 4 on pages 9 and 10. So I'm going to show you on GeoGebra so you can see what it looks like properly kind of drawn to scale. And then I'll just show you what my sketches were in a second. Just double check if there's any questions there. So the first graph we've got is y equals x. And what I'm just going to show you first is what the graph of modulus of x looks like. So we just click this and I'll take this away. This is what the graph of modulus of x would look like. So I've got the original graph of y equals x, so it's just our straight line there. Okay, so just going through 2, 2, 4, 4, 6, 6, etc. So we've got our normal y equals x graph, but what happens is for all the values, for all the positive values of x, you get positive values of y. So for x is greater than 0, the graph still looks the same. However, when x is less than 0, you get negative values of y, because obviously here x equals y. So for numbers like -2, -4, we have to reflect these numbers, because now what happens is when you put in x as -2, or the modulus of -2, it's just positive 2. So all we do here, draw our graph of y equals x, so that's what y equals x looks like, and then we just reflect any bit that's below the x-axis in the x-axis. Okay, so that is a graph of y equals the modulus of x. The next example is y equals 3x minus 2. So this is our graph of y equals 3x minus 2. Remember, all things we've done before, we want to find out where it crosses the y-axis. We sub in x equals 0. And if we want to find out where it crosses the x-axis, we sub in y equals 0. So when x is 2/3, just zoom in a bit there. When x is 2/3, it's crossing the x-axis. When y is -2, it's crossing the y-axis. So what we do is we just simply reflect anything that's negative in the x-axis. So all of this below the x-axis just gets reflected. So before, you would have had x when x is -2. Sorry, when x is 0, you would have got -2 before. But now what happens when you put in x as 0, you get -2, but then you have to take the modulus of it. So it's just going to be positive 2. So this is the graph that we get. Okay, so I'll just take off the original, and that's the graph that we're left with. So it's always best to just sketch your original graph without the modulus and then do it with the modulus. The final example in this part for modulus of f of x graphs is when we've just got a quadratic. So let's see what happens here. So this is concerning example x squared minus 2x minus 3. So you'd want to factorize this first. So this would be x minus 3 and x plus 1 when you factorize x squared minus 2x minus 3. So you can plot the roots of 3 and -1 on there. It also crosses the y-axis at -3. Okay, so when x equals 0, you get -3. So now let's consider what happens when we do the modulus of this. Now, for x is less than -1, we were getting positive values anyway. And for where x is greater than 3, we were getting positive values as well. So the graph remains unchanged for x is less than -1 or x is greater than 3. However, what's happening between the -1 and the 3? Before, you got negative values, but now because it's in the modulus, those negative values become positive values. So where you had this minimum point before, you've got this local maximum point. Note that this isn't a quartic graph. It's not that -1 and 3 are turning points. So it shouldn't look as kind of curved, that kind of curvy shape that you would normally do with like a quartic graph, or where you have turning points in the graph. What you should find is that it's kind of a bit more sort of straighter here, a bit kind of more like a point that you've got, rather than kind of like a turning point like we're used to with the quartic. So just watch out for that. Okay, make sure as always you label all key points on your graph. So you label that -1, you label that 3, and you label that y=3 as well. Okay, before that was a -3. So before you put an x is 0, you got -3. But now because you're taking the modulus of -3 is just +3. So let me know if you've got any questions there. What I'm just going to quickly do is show you now what the sketches would look like. So I'm just going to take you off of GeoGebra here. So we should see back. We should be back on the OneNote now. So you can see here the graph. So if you just want to sort of do the sketches for your workbooks, no, we don't have to obviously be anywhere near as accurate as we do on GeoGebra, but I would recommend use GeoGebra, check what graphs look like. So these are our first two examples that we did. So the y=x, and then the y=modulus of x to the right of it, and then y=3x - 2, and then the modulus of 3x - 2. Yet again, important points that we're getting those x-intercepts and we're getting those y-intercepts in there as well. And then this is what our quadratic example looked like. We sketched the original quadratic. We've got our roots of -1 and 3. I should definitely have the -3 on there as well. And then when we sketch it here, we should have a 3 there. Okay, let me know if you've got questions. I'm going to skip the next couple of pages because I want to focus on the equations in the next lesson. So these next few examples focus on pages 13 and 14. So we've just looked at sketching the graph of y = the modulus of f of x. Okay, so just sketch your f of x and then reflect any part of the graph below the x-axis. What we're going to look at now is y = f of the modulus of x, which is different. Okay, with our first example, we were basically working out the value, but then we took the modulus of the whole thing. Now what we're doing is we're taking the modulus of x and then working it out. So you're going to get different results. So to sketch graphs of the form y = f of the modulus of x, what we do is for x is greater than or equal to 0, we just sketch that graph as normal. Okay, so everything basically to the right of the y-axis is just going to look as it normally would, because you put in x = 1, the modulus of 1 is still +1. So the graph is still going to look the same. However, what's going to happen on the left-hand side of the y-axis is when you put in -1, well, actually what you now are doing are putting in +1. When you put in -2, you now put in +2, basically. So then what you're going to do is you reflect what you've drawn in the right-hand side, right to the right of the y-axis. You're going to reflect that in the y-axis. Okay, so you draw your x is greater than or equal to 0 to the right of the y-axis, and then you're going to reflect it in that y-axis, because x is 1 is going to have the same y value as x is -1. X is 2 has the same y value as x is -2 when you take the modulus of it. So I'm going to show you two more examples on GeoGebra. So we've got x squared -3x - 10, and we've also got the graph of sine x as well. So with both of these, we're going to look at what the modulus of f of x looks like, and the modulus, and f of the modulus of x. So there is a distinct difference between these two graphs. They are definitely not just the same. So let's head back over to GeoGebra. So bear with me a second. Do let me know if you can't see anything that I'm displaying. So you should see GeoGebra back again. And what I'm going to do is the first example that's in your book there, which is x squared minus 3x minus 10. So in the booklet, what we need to do is show both what the modulus of this is. Ignore all my things on GeoGebra. I've got as a of x and r of x. That's because I've got so many different functions here. Okay, in our booklet, it's just f of x. So f of x is x squared minus 3x minus 10. So factorize that to x minus 5 and x plus 2. It's got a y-intercept of minus 10. Firstly, we just find the modulus of f of x. So just reflect any bit that's below the x-axis into the y-axis there. Sorry, reflect that into the x-axis, I should say. So just everything that's below is now above. So that's what your modulus of f of x looks like. Now what we're going to do is see what happens when we do the modulus of, sorry, the f of the modulus of x. It's a lot harder to say these things than when you're writing them down. So what happens is everything to the right of the y-axis stays as it is. Everything to the left gets reflected. Okay, so for x is 0 and greater, then everything stays as it was. Okay, because you put in x is 2, take the modulus of 2, it's still 2, so that remains unaffected. However, now what happens when we put in, let's say, x is minus 5? Well, we take the modulus of minus 5 and we get positive 5. So this stays, so this gives you the same y value. So when you put in 5 and minus 5, you get the same y value. When you put in 6 and minus 6, you get the same y value. So I hope that makes sense. Do ask me if you're not sure. And then finally, we've got g of x equals sine x. Now, just to note, the question in your booklet is doing this in degrees. On GeoGebra, it will plot in radians. There is a way to kind of get it to look as do in degrees, but I would have to change the scale of everything else here, so that would make it a bit problematic. So this is just in radians, so you can see there it's crossing there at roughly 3.14, which obviously is pi radians. So this is our graph of sine x. When I do the first example, which is just do the modulus of g of x, what I just do simply is just anywhere where it's below the x-axis, it just gets reflected. So you just end up with this, okay? With the modulus of g of x, unless there's any kind of plus or minus parts after it, it should always be above, all your graphs should be above the x-axis, okay? Obviously, if we had the modulus of sine x and then say take away 5, then that will make a difference. You would have parts below the x-axis. But when we're just taking the modulus and there's nothing else there, everything should be above the x-axis. Finally, we do sine of modulus of x. And what we do here, we just draw the graph as normal for x is greater than 0. So this is just our normal sine graph to the right. But then we just reflect all of that in the y-axis as so. Now I'm going to show you now what that looks like when I just do the sketch. So obviously you're not going to draw it as neat as that in the exam. So let me just show you what I would draw. Just give me a second. Okay, right. Sorry, it's the last time I'm going to switch over now. Okay, so this is just what these graphs look like when I just do the basic sketch. Okay, so firstly, draw your y equals f of x, so you know what the graph looks like. You know, factorize it first, get those intercepts on there. And then you've got the modulus of f of x to the left. So just all the parts that are below. So between -2 and 5, where it's gone below the x-axis, that's now above the x-axis. And then we have y equals f of the modulus of x. So everything that's a positive value of x stays as it is, but then just reflect that on the y-axis. And then for our sine x. So you might just want to draw a sine graph just to remind yourself of the shape first. Basically, anything that's below for modulus of g of x just gets reflected above. Make sure you get things like your intercepts on here like this. And then for g of modulus of x, you get this nice looking shape here, where just from 0 to 360, draw one wave as normal, and then just reflect that in the y-axis. Let me know if you've got any questions. Just before we finish then, rather than me go through this example, I'm going to give you 2 or 3 minutes to work through this, and then I'll pop up the answer. So have a go at this question, and then I'll show you the answer, and then answer any more questions that you've got. So rather than me go through this example, give you a break from hearing me talk. Have a go at this question, and then I'll show you the answer at the end. This is not a particular quadratic or cubic. It's just a function we don't know what it actually is. So we just go from the sketch, and we just want to make sure that we show those key points. Okay, so what has happened to A here? What's happened to B, etc.? What's happened to C when you do the modulus of h of x and h of the modulus of x? So I'm going to give you 3 minutes to have a work through that. So just have a go at that in your booklets. You might want to do it in pencil just in case you're unsure, and I'll show the answer in a few minutes' time. So whilst you're doing this, if you do have questions, pop them in the chat. A couple of minutes. Okay, 1 more minute, and then just show the answers. Do let me know if you want a little bit longer, or say you've got any questions. Okay, so here is the answer then. So just mark along with this one, and just making corrections that you need to. So for the first one, all the parts below the x-axis just got reflected. So before up to -7, everything was below the x-axis. Now it gets reflected above, and then from the 3 onwards, then you should see that reflected. So you kind of go up to that local maximum, which will now be 6, +5, and then you kind of tail off for this asymptote here at the end. For the graph of h of the modulus of x, then just draw that right hand side, stays exactly as it is. Okay, I know mine looks almost a little bit different there, but still the key points are all there. So everything from that 0, 11 to the right all stays the same, and then just simply reflect that in the y-axis. So pretty much, that's why we don't need to draw the minus 2.5 15 point again, okay? Because at that point's irrelevant now, really, because basically you're just taking the modulus of x anyway. So you just draw it like this. Okay, so now what you're gonna do, have a look at the handing questions. Okay, I could have put this a bit tongue in cheek here, but I know sometimes people say, well, I can't remember what y equals natural log of x looks like, or y equals 1 over x looks like. Okay, that will come up in some of the questions. So just if you're not sure, just have a look back in the booklets. I believe that the graph of natural log of x was in booklet 3, or it was at least the graph of log x anyway, was in booklet 3. So just have a look. You've got the internet available to you, so if you have forgotten that, do the research yourself. So if there's any questions, I'll take them now. If not, we'll leave it there and see you tomorrow for when we're starting equations.